Welcome to our afternoon lecture. My name is Brian Kurth from the Math Department, and I'm pleased to welcome you to our second STEM talk for the semester. STEM, as you may know, stands for Science, Technology, Engineering, and Mathematics. Our lecture today will be given by Professor Chuck Bales and Jordan Murray. They will be discussing industrial applications of 3D printing. Chuck is Associate Professor and Coordinator of Mechanical Design and Drafting and Computer-Aided Design over in T-Building, and Jordan Murray is a student here at Moraine Valley. They will talk for about 45 minutes or so, and then we should have some time for Q&A afterwards. So without further ado, I give you Chuck and Jordan.
All right, good afternoon, everybody. How are we doing? All right, good. Well, my name is Chuck Bales, as Brian introduced me. Jordan Murray is a lab aide of mine that's been working with me for, what, 2-3 years now? Something like that. Yeah. And he is working intently with our additive manufacturing in our department. We have a number of 3D printers, additive manufacturing machines, and Jordan has been working those. So I wanted him to help me with the presentation here because he has maybe even a better feel for it than I do. So I'm going to get you started off with a little bit of background talk. So first I want to kind of paint a bigger picture to let you understand where 3D printing and additive manufacturing comes from. So really, the term right now is additive manufacturing. 3D printing is only one aspect of additive manufacturing, the actual printing part of it. This is a full-fledged manufacturing process. Before additive manufacturing was around, we really had three processes that we use for manufacturing parts. We had joining, which involves welding or screwing parts together. We also had subtractive manufacturing, which includes cutting, machine tool cutting. And we had forming, which would be casting and forging and operations like that, injection molding. Additive manufacturing is a full fourth member of the manufacturing processes here because it manufactures in a way that is different than all the other methods. And so it creates some added benefits, some ways that manufacturing and designers and engineers can leverage to go in completely different directions, as I'm sure you're going to find when we go through the industrial applications. This is really an exciting time because this is part of the fourth industrial revolution. We are actually involved right now in the process of going through the fourth industrial revolution. The fourth industrial revolution includes Wi-Fi, nanotechnology, cybersecurity, and additive manufacturing. And so all of this is kind of coming together, converging to really give engineers tools that 10, 15 years ago were not available at all. 3D printing kind of fits in with this Industry 4.0 scheme with robotics and the Internet of Things because 3D printing allows us to have distributed manufacturing. So if I want to print something and I'm on a ship and I need to print a new rudder or a new propeller, I can have the files emailed to me and I can print those files on the ship. This is also being done in space. We have some examples here of parts. This is a sample part that was actually sent up to the International Space Station and printed. The astronaut up there needed a ratchet, a special type of ratchet. It was designed on Earth, emailed up as an STL file, and then they printed it, and they had a 3D printer on the space station. It's a working ratchet. So this is, as I said, part of the fourth industrial revolution, what's known as Industry 4.0. Okay? Just to give you a sense of the additive manufacturing market, these graphs are just a couple years old, and I assure you that the trend is still upward. But in 2013, over a third of the additive manufacturing market was using 3D printing for final production parts, and so 34.7%. And if we look at sales estimates of industrial machines for additive manufacturing, again, in the 2013 report, we're up to nearly 8,000 machines. And again, I assure you that that trend has continued up. You might see a little blip right here, of course, around the 2008 time period, and I'm sure you know what that is. That was the market correction. So that's why we have a little downward trend, but it continued back up again. Now, of course, when we talk about a fourth industrial revolution and we talk about where 3D printing fits into the manufacturing, engineering, and design landscape, I'm sure you've heard and you are aware of the disruption that this causes. So 3D printing is not without causing problems. The problems that 3D printing causes are disruption to our normal supply chain and logistics, how we get raw materials and how we distribute manufactured materials. There is huge intellectual concerns because now I can scan a part. I can do a scan of a part, make an image of that in my computer model, and then I can print the part as if it's mine. So I don't need to buy a part or a machine. As long as I can just get it and scan it, I can print it. So there's intellectual properties concerns. There's also issues with design cycles where now the design cycle has been greatly reduced. What we call the design cycle now, it's undergoing time compression. So whereas it would take literally years to design certain things, now that time is being compressed and engineers are having to or are able to design in a much shorter time frame. That has both positive and negative effects, but it's definitely a disruption to our normal state of affairs. And finally, entry barriers. This is a disruption, but it's a good disruption. Now we can enter the manufacturing market, and we don't have to worry about buying expensive machine tools or finding the area and the expertise for a foundry. All we need to do is buy a 3D printing machine, an additive manufacturing machine, and we can go ahead and get into the market for manufacturing with our designs. Some of the designs and some of the applications that Jordan's going to go through, you'll see these are small shops that, boom, they just appeared. They're printing things, they're selling things, and you know, it's a great way to get those small areas out there to start producing items. So I do want to talk a little bit about, because we are going to talk about the individual processes for additive manufacturing, I do want to take a little bit of time just to go through these. I'm not going to go into each one in detail because that would be 2 or 3 more lectures. But there are 7 classifications standardized for additive manufacturing processes. Okay? And they fall under the category of liquid-based, solid-based, or powder-based processes. In the liquid-based process, we're starting with a liquid. The material that we're forming into a solid is starting as a liquid. So these include vat photopolymerization, material jetting, and material extrusion. Currently in our labs over in the CAD department in the T building, we have a vat photopolymerization machine, and we have 2 material extrusion 3D printers. Under the solid-based, the material that we're starting our additive with is a solid. So it could be, typically it's sheets, could be sheets of paper, could be sheets of aluminum or sheets of any other type of metal. But here we have a sheet lamination process and directed energy deposition with the wires. And finally, and this is the powder-based area, is really where metals, metal 3D printing is excelling. In the powder-based area, we have materials, we're starting with powders to get our finished solid object, 3D printed object. So this includes binder jetting, powder bed fusion, and directed energy deposition, but using the powder to start with. So that's our 7 standard classifications. Any process that is out there in the market is going to be based on one of these 7. They might not use the same name. So like you'll hear the terminology selective laser sintering. Selective laser sintering is the trademark term for a powder bed fusion process. We have a fused deposition modeler in our labs over there. Fused deposition modelers, or FDMs, are material extrusion machines. So each company has their own trademarked and copyrighted name for their machine, but they're going to fall under one of these 7 categories. When we talk about materials, this is really one of the linchpins that set off the market in terms of the industrial applications. In the old days, back when 3D printed started around 1986, when it was first developed by Charles Hull, plastics were the only way to go. Okay, so we had plastic. The processes that could develop plastic include vat photopolymer, material extrusion, material jetting, and sheet lamination. Okay, that kind of transitioned to more of a ceramic and composite. But once the development was achieved for the powder processes, powder metallurgy is actually a defined science, a manufacturing process that's well resolved. So it's been out there in the world for a long time. When it was understood how to develop, how to create parts with 3D printing powder, that took on a whole new avenue. And that's really the starting of the industrial look at 3D printing. Because now we can use metals to actually print functional parts. Okay? Before we could only print with plastics and some ceramics and composites, which obviously from a functional point of view is going to be very limiting. All right? Plastics aren't as rigid and durable as metals. So in the metal category, we can actually print with the material extrusion process, sheet lamination, directed energy deposition, powder bed fusion, and binder jetting. So all of those are processes that can use powdered metal. They also use powdered plastic, but really the metal is the important distinction between when we went from a full industrial process here. So the last couple of slides I want to talk about where additive fits into the manufacturing scheme. Okay, so remember we have 4 manufacturing processes. We have subtractive, joining, forming, and now additive. So what's going to make a designer or a company decide, hey, yeah, I want to go and try out this additive manufacturing? So whenever a designer is trying to decide what type of manufacturing processes they're going to use for their part production, they're going to look at a couple of different things. They're going to look at the volume of production. Is this a high volume or is this a very small, maybe 1 or 2 volume of production? What is the level of customization? Are there standardized parts that we can produce, thousands of? Or are these like we need to produce 1 for Joe and 1 for Mary, and the 2 are going to be, very different? What is the part complexity? Is it a very complex part, so that rules out casting and forging and maybe only leads to machining? What's the part cost? And this is the cost for the market, right? Is it supposed to be a high-end part, or is it going to be kind of a bargain basement dollar store kind of part? And finally, what are our production capabilities in our shop? All right, do we have the material? Do we have the room? Do we have the expertise? Are we going to have to shop out for help with this? So all of these factors and more go into the decision-making process of, well, which process are we going to take? Where additive really excels is in these 3 areas. Okay? Additive manufacturing is superb for low volume because I can literally print 1. I don't need any additional setup. I don't need any tooling, any molds. I can just print 1 part or 10. Okay? High customization. Right? There's companies out there right now, which Jordan will go through, where you can have your shoes 3D printed. They will mail you a box of styrofoam for you to step in with your bare feet. You mail that box back to them, and they print you customized, 100% customized shoes that only fit you. So the customization level is off the charts for additive manufacturing. Finally, in high complexity, you can see an example of this part right here. This is actually a part taken from an aircraft. Okay? The original part is over here, and you can see the original part is kind of blocky and kind of basic. We have a square section right here that's kind of truncated, and we have some support ribs. This is designed so that we could manufacture it, right? In a casting operation or a machining operation, to some extent we have to compromise our designs to the process. And that's not good. Engineers, I'm an engineer, and I have problems with that. I don't want to compromise my design. I want to design it, engineer it, analyze it, and make it exactly as I dreamed up. Well, with additive manufacturing, we can actually do that. So this is the additive version of this, where it's gone through a process called topology optimization, where we load this virtually in our computer with the forces that we expect to see in the aircraft. And then we let the computer churn away to decide where we need material and where we don't need material. Now, if I sent that drawing to a machine shop and said, hey, you know what, I want you to print this for me, or I want you to machine this for me, they would laugh because it's not machinable, it's not castable, it's not forgeable. But with additive manufacturing, it's no problem whatsoever. Okay? So the high complexity is perfect for this. A couple of things that we have to watch out for. Additive manufacturing actually has significant production time. Okay? So this part may be great to print, but it may take 10 to 12 hours to print. Okay? So that's one thing. Not necessarily too slow. Machining it would also take a lot of time. But we got to remember that. The second thing is there's often, especially in the case of metal 3D printing, there is often post-processing that needs to be done. So the part has to be sintered to make sure it has full density. The part may have to be heat treated. Those are going to add hours or days to the process. So it's not just a one and done, hey, let's print it and move on. You know, there's hidden time scales in there that we have to be aware of. So that's the additive advantage. That's where companies are really starting to leverage additive manufacturing to shoot forward and to really develop parts that we've never seen before. Literally, we've never seen these before. The applications that Jordan's going to go through next, they fall into three categories. Okay? We have rapid prototypes, rapid tooling, and rapid manufacturing. Okay? Rapid prototypes are parts that were printed as prototypes. So if you're developing a cell phone, rather than go to a meeting with a picture of your cell phone, or maybe a computer and you have everybody stand around and look at it, you can print the cell phone in color and bring to the meeting. So everybody can feel it, see how it weighs in their hands, see what it looks like. So those are prototypes. They're used in architecture as well to print architectural models before they commit to the construction. Rapid tooling is where we use 3D printing and additive manufacturing to print tools for manufacturing. Tools could include molds and dies. They could include jigs and fixtures. Oftentimes, rapid tooling is done with plastic parts. And so actually, rapid prototyping and rapid tooling were the first true industrial applications to 3D printing. And now we're at the new age of rapid manufacturing. This is where we're using we're using additive manufacturing to print functional parts. That is, parts that you can see in airplanes that you get on, parts that you can see in cars that you get in, okay? Parts that are actually finding their way into our common everyday appliances and, you know, things that we use every day. These are mostly metals, as I said, and that's really when we started developing metal production processes in the early 2000s, that's where this kind of kicked off. All right, so again, just trying to steer you in the direction of where Jordan is going to lead you next. Companies look at developing additive manufacturing content in 4 different stages. Okay? These stages start out with that testing stage, right? Getting your toe in the water, seeing how it feels. And that includes the low volume parts. These are made directly from CAD, and usually they're rapid prototypes or rapid tooling. Okay? Where the company is not quite sure whether this is going to work, and they try it out. Next, they get into direct part replacement. So this is where we avoid complex manufacturing by just printing things. Now, I was at a conference last year with a fellow from Caterpillar, and he was head of the additive manufacturing department at Caterpillar. And what they're finding is their old tractors that they no longer have the tooling for, that they no longer support, when they have a contract with that buyer, that they will always support that piece of equipment that they purchased. But they don't have the tools and dies for them anymore. So when something breaks on these old tractors, now what they can do is go get the drawings, convert it to a solid model, print the part, and mail it to them. So they can get all that done. The third area, the third stage, is complex parts that simplify assembly and enhance reliability. What we're talking about is printing parts that are fully assembled to start with. And then finally, the fourth stage of additive manufacturing application is where we're redesigning everything. Right now, GE, Boeing, and Airbus are already at stage 4. They're redesigning things from scratch, without any preconceived ideas. So companies are arrayed along these 4 stages. Early adopters are all the way up at stage 4. And now I'm going to turn you over to Jordan.
Thank you. Now for the fun part of the lecture. For the rest of the lecture, I'm just going to basically do a little show and tell. We're going to tell you some specific examples of where 3D printing has been used in industry. And everything that you're about to see are actual parts that have actually been created. Nothing you see here is an idea or a visualization. Everything is true and has been printed and is being used. So first I'm going to start off with the healthcare industry, which is a major adopter of 3D printing because healthcare is very highly complex and it uses a lot of highly customized parts. Each individual is a different person, has different needs. So healthcare really fits well with 3D printing. First example is this young boy, Alex Pring, who was born without his right arm. His parents were faced with a $40,000 bill for a prosthetic arm, which they couldn't afford. So they were stuck with nothing, basically. They couldn't afford the prosthetic arm until engineers at the University of Central Florida were able to design and print a prosthetic arm for him, which he can control with his mind for just $350. They did the whole thing in just 7 weeks. And they're hoping that the design, which they put online for free to everybody to use, will sort of be a wake-up call to people who need prosthetics, that prosthetics shouldn't cost $40,000. We can do this for a fraction of the cost. And now Alex is able to shake people's hands and hug people with his hands, and he's living a sort of normal life now. On the right, we have hearing aids, which are taken from scans of your ear. And you can tell each one is slightly different. Every single hearing aid is designed to fit directly into your ear, specific to your ear. So these fit much better than traditional ones, and the company doesn't have to have their laborers sculpt these by hands anymore. So now they can increase their productivity, I think like 8-fold, they said in their article. So next, we have, which I think is a really cool application. We're able to print human organs, more or less. So the researchers printed a scaffold, which is like sort of a mesh of the organ that they want to create. And the mesh is printed with biomaterials, such as like gelatin or something that will dissolve away. And laced within that mesh are stem cells taken from you, the patient who needs this organ. So these organs are guaranteed to fit within you when they're ready to transplant. And once these are done, once the scaffolds are ready, they are put in a bath and left to incubate for 2 months. And then after that, they're ready to go. They're living, they're working. And I think 3 days ago, they started printing skin, right?
Yeah, on your arm, they can print skin. So they have 3D printers that move with your arm.
Yeah.
In situ.
Pretty cool stuff. Casts also are another great example of highly customizable 3D printed parts. The casts are taken, again, from a scan of your affected area. And since the cast is plastic, you can wash it, you can take it in the shower, you can scratch through it, and it's a lot cheaper. This, depending on the material, that's around $6 of material as compared to a cast which costs, what? A lot more than that.
Yeah, probably thousands.
Thousands?
In our healthcare industry.
Gotta love it. I'm going to start with Mia Gonzalez up there on the top left. Oh. Be careful with this part. It's very fragile. Mia was born with a condition known as double aortic arch, which is where a vascular ring will wrap itself around the trachea or the esophagus and limits her airflow. She had troubles breathing when she was a kid, and this is a very complex surgery that she needed to undergo in order to fix this. So what you're holding right now is a model of the heart that was taken from CAT scans of her heart, which was used to make a 3D model. And the surgeons would carry the heart, which is much larger there. They would turn it over, and they could see each individual vein, and they can see where the problem is with her heart. So they would carry it around, and they were able to kind of think visually in their head before they actually, before she underwent surgery. They were able to kind of visualize where they needed to go and what they needed to do. So they kind of knew what to expect before they actually did the surgery. And now, thanks to that, she's made a full recovery, I think, right? And she's now living a healthy life. In the center, we have Gigi the parrot, which you might have seen through Facebook or something. Gigi was found abandoned in a Brazilian house, and she has a beak defect, which meant that her beak would just continually grow. And she couldn't eat, she couldn't climb normally, she was very malnourished. So veterinarians took her in and printed this titanium beak for her, and now she is able to eat correctly, and she's much healthier. The man in the bottom right, or bottom left, fell 3 stories and landed on his head and cracked part of his skull. But the doctors in China were able to print a titanium mesh implant, and since the titanium is porous, it allows the bones to, it facilitates the regrowth of the bones. And like Chuck was talking about earlier, the shoes that are 3D printed, the red sole part right here is what's actually 3D printed. So when they get the copy of your feet, these shoes are printed exactly to fit your individual foot. And athletes can really take advantage of this because the materials that we can use with 3D printing are a lot more advanced. We were able to sort of mix plastics together in order to get just the right amount of springiness or the right amount of flex in your soles. And some of the cool parts of this is you don't even need to have CAD knowledge to do some of this. You can go on websites like My Mini Factory, GrabCAD, or Thingiverse and download parts to just print right from home. And speaking of that, this company will print you a pair, or you print the headphones, the company will ship you the electronics that you need. And for, I think, like $46, you can get a decent pair of headphones. Maybe. If your internet connection's good, you'll get headphones. Cool. So, yikes. All of these designs you can print right at home for free, basically. Well, not for free, but at a lot cheaper cost than having to pay $200 for a pair of headphones. And if you want, you can design your own. Somewhere down here. You can design your own headphones to fit you. You make them your own color, your own style, however you want to fit. I thought that was pretty cool. Another industry that's really booming is high-end custom bikes. We're able to, well, the company Robot Bike has a program where you can enter in specific dimensions that you want for your bike, and then based on those few simple dimensions, the joints are created and printed exactly for you, exactly for the bike that you specified. And when we use this technology, along with topology optimization, we're able to create really lightweight frames. Like the frame that we have pictured here in the top left or top right, the frame itself only weighs 2.5 pounds because we're able to create highly lightweight parts that are just as strong as they need to be. And we're also able to print houses to some extent. Using the same technology as regular 3D printers.
This is in China right now.
Russia.
Russia. Well, Russia and China are
They're both doing.
Yeah.
This was printed. You can tell there's snow in the background. This was printed in one of the harshest winters in Russia as a demonstration. So it's in a tent right now as it's printing.
By the way, this is a fused this is a material extrusion process, fused deposition modeling, and it's just spitting out like concrete that's going to dry.
Totally insulated, just like a regular house.
Yeah, think about Puerto Rico right now,
Exactly.
where they might need houses shortly.
Perfect for extreme weather conditions, low-income housing, refugee camps. This is printed in less than 24 hours. It's 860 square feet. Not bad.
Yeah. Not all the designs are that circular format. There's some that are rectangular and stuff. So it's not really, there's not really a design limitation on this.
Like you can see, this one's more rectangular. Pretty cool. Now we get on to manufacturing. And like Chuck was saying, 3D printing has really disrupted manufacturing. Now we are able to create parts that we previously have not been able to create before. And a perfect example of that is on the left, we have injection molding molds. And when you use injection molds, the parts have to cool off as quickly as possible. So one company printed their molds with what's known as conformal cooling channels. And the red tubes represent the channels where coolant will flow through. And because we can print the parts with these channels through the actual mold, you can cut the time it takes for your parts to cool by half. I think it took 10 seconds versus 22 seconds. So you're increasing your productivity by 2. You're doubling your productivity. The left side shows the traditional means, which is basically just drilling a hole. You couldn't do much else besides that. But with 3D printing, we can create channels inside the part itself. And with jigs, we can create highly complex geometry to accommodate more complex geometry. This fixture, or well, the part that it's holding right now, you can tell it's sort of bent. It's got all this weird geometry. It'd be hard to bolt this down to do quality assurance. But with 3D printing, we can match those curves perfectly, and we can use the coordinate measuring machine that they have, and quality assurance is a lot easier to do. We can also use 3D printed jigs for machining or for drilling, for woodworking, because traditionally when you make jigs, you have to make sure that you're drilling the holes in the exact right spot, or otherwise you just messed up your jig and every part that you make. But with 3D printing, they come out of the printer. Oh, yeah. They come out of the printer correct. You know that they're correct because you designed them correctly, hopefully. Another area where we're using this is assembly fixtures and jigs. So this tool was originally made by BMW with metal. It was very heavy and very awkward for the assemblers to use. If you imagine lifting that part up made of like hard, cold metal hundreds of times a day, it'd be stressful on your joints. So they printed a more ergonomic model that's way lighter than the previous fixture that they used, which led to an increase in the productivity of their assembly lines and faster production. We're also able to print the molds themselves. The part that's going around, the metal part, was printed with a 3D, or was cast with a 3D printed mold. So the green parts here on the right were actually 3D printed. And since these parts are 3D printed, we can create them much faster than before. Typically, molds like that would take something like 2 weeks to arrive at your shop, but now
very expensive.
Yeah, and very expensive to machine. But now we can print them overnight or in a couple hours, and we can start producing things much faster.
Yeah, design changes can be done right on the fly. The other part that's going around, the small blue clip, that was injection molded from plastic 3D printed molds. So the molds can be done in plastic, or they can be actually done in metal now. So, you know, both of those parts, the Z Corporation, the large shape, that's aluminum, and that was cast with aluminum, but from 3D printed molds.
Right. Actually forgot to pass this one around too.
Oh yeah.
This isn't the same headphones that we were talking about earlier, but everything in the headphone is 3D printed. These are all 3D printed components. And they work. You can plug them in. All right. The next area we're going to look at is automotive, which is really, especially with Formula One, is really counting on additive manufacturing to create lightweight parts. You can tell every kilogram that we save with Formula One has the potential to earn their racing team $120,000, because 1 kilogram can be the difference between winning or losing a race. And like we were talking about with manufacturing, 3D printing for the automotive industry is huge with creating prototypes of their components. Where it would typically take weeks or days to get parts back from a machine shop, we can print them overnight, have them in the wind tunnel test by the next day. And I believe the part on the left, the front spoiler, is actually being used in the picture below. It's the blackish parts down here in the front.
Yeah, F1 uses, they actually race with 3D printed parts. Which company, one of the racer groups is they have 3D printers on trackside.
Right.
So if they need to
McLaren.
make minor changes or print something else, they can print it.
Right, which we'll show them. Just this year even, Ferrari announced that they're going to start using 3D printed pistons in their Formula One engines. And they're going to reduce the number of parts because they don't need to assemble it in the same way. They can just print it right out of off the printer and take it into their cars. And they're going to make it lightweight by using a honeycomb structure on the inside, which makes the part much lighter and saves even more weight. And like Tuck was talking about earlier, McLaren, there it is, has a 3D printer that they take to their tracks. There we go. I meant to do that. These are all parts that came off of their printer that they used. So they can print parts that come from their design lab in the UK and email them anywhere in the world that they're having their race. And if the weather conditions or the track conditions are sort of different than what they were expecting, they can print a part overnight and install it on their vehicle the next day for the race. It's kind of like cheating, isn't it?
Yeah, well, I think they're all going to start cheating.
Pretty much. Michelin, the tire company, has introduced a new prototypical tire that's airless and is 3D printed using a biomimetic design, or mimicking biology. The tires are 3D printed, and they actually will send an alert to you when they need to be treaded. And these are completely recyclable materials. So when you're done with your tire, or when it needs to be thrown out, it will degrade naturally. The parts are all recyclable. And when your tires do need to be retreaded, they can just print it right back on. You don't need to buy whole new tires. We'll just print what you need. Even entire cars are being 3D printed. This company, Local Motors, everything in that car except for the mechanical parts is 3D printed. The plastic that they use is carbon fiber reinforced ABS plastic, and very hard, or very lightweight, very resilient. And
wasn't the design, didn't that come from
was it a design
competition?
contest? Yeah.
It was a design contest.
I couldn't remember that, yeah.
And the winner got their design as the car.
And I think like $5,000.
Yeah, not that much.
Yeah, kind of.
You can see Jay Leno driving that around. His video series, he's driving one of those.
That was a good video.
Yeah.
I think the car is electric, and I think it's something like $10,000, $15-ish thousand.
Yeah.
Not too bad. Top speed of 40 miles an hour. It's got a range of 100 miles. Not too bad. Which leads us into the final area we want to look at, which is space, or in aerospace, airplanes. Aerospace is really looking to make their planes more lightweight in order to save money on fuel. And they're starting with brackets, the things that hold the plane together. So, way ahead of me.
This is the original bracket design. Was this from Airbus or Boeing? You remember?
I think it was Boeing.
Okay, this is a Boeing bracket, right? And you can see it's big and thick and, you know, blocky because that's what we could manufacture. So they had a competition on GrabCAD to redesign it using topology optimization. So I'll pass these around, and they went with one of the topology optimized parts, the one that Jordan's showing on the left-hand side there. That's the actual part that is going into airplanes, greatly reducing the weight, because there's hundreds of these in an airplane, maybe even thousands. So
Yeah,
when you
imagine the entire
reduce,
cabin is
so I'll pass these around.
redesigned.
We printed all these in.
Maybe we should do like one at a time.
We printed all these in our lab.
And the part here on the right is the partition, which separates the classes of the plane and where the flight attendants sit. The partition, all of that is 3D printed in separate parts and then joined together. The partition is 45% lighter, and I think per partition it saves like 9,000 pounds of jet fuel per year. So with an entire cabin full of those things, imagine how much less fuel they'll need to use and how much cleaner their planes will be. NASA on the right side is even using these for their rocket launcher or rocket propellers. This turbo pump here, the part that pumps the fuel through the thrusters, that's all 3D printed, and they're using these in rocket launchers. On the left side, we have a fuel injector assembly, which is made by GE, and the fuel injector actually uses, I think, like 40% less parts. It takes 2 days to 3D print as compared to, I think it was 2 weeks.
Yeah.
So they're really saving time and money.
This is an example of that fourth stage of development where you're redesigning things from scratch. So the turbo for the rockets, that was designed from scratch. This is not manufacturable in the traditional ways. It can only be manufactured additively. But there's great weight reduction, there's great assembly parts reduction, also the fuel injector on the left-hand side. So you have a lot of savings going on here, a lot of efficiencies that are being gained.
Right. This next part's really cool. It's one of my favorites. That turbo pump we saw earlier, this is a video of it being tested along with other 3D printed parts. Make sure it's not too loud. Much of that rocket engine is 3D printed. And that was at full full test, full cycle. 20,000 pounds of force, or thrust force, and it worked just well, just fine. And like Chuck was talking about earlier, NASA has a 3D printer in the International Space Station. Astronauts are able to print all the parts that they need right on the International Space Station. So you can imagine, if you need a part, you can't go to the store and get a part in space. You have to wait for a rocket to come and bring it to you, which can take months or years and is very, very expensive. So now, astronauts are able to print exploratory tools or tools that they need to make repairs right on the International Space Station. Don't remember which this one was.
The 3D printing industry is still in its infancy, but that has not stopped one company jumping forward into the future and planning their own 3D printed shelters for other planets. French firm Fabulous have designed a conceptual shelter dubbed Sphero that would be 3D printed on the Red Planet using locally available materials. The designs are in response to NASA's competition, which is seeking new ideas for 3D printed Mars habitats.
All right, sorry that was kind of quiet. Earlier this year, NASA announced a challenge competition for students in universities to design 3D printable habitats for exploring Mars, for human colonies. And this one company in France, this is their design that they submitted. They call it the Sphero home, or the Sphere home. And the robot that they've created has 2 arms. One of the arms digs in the Martian soil and extracts iron from the iron oxide-rich soil and uses that iron to print these two shells, these 2 holes on the outside. The other arm actually does the printing. The robot also has a drill which can dig for the permafrost water beneath the surface, and will use that water as insulation from the ultraviolet waves of the sun. Can't remember the square footage of the house, but I think it was around 900 or 800 something square feet. So it's about the same as the house that we saw earlier. Pretty decent. I think the winner was actually, were they from Korea?
I don't know. I didn't see anyone. I didn't see.
I
the
don't remember
winners.
either. They didn't end up winning, but they had a really good video on their visualization.
Okay.
Send this back to Chuck.
So I'm just going to finish up the talk, and then we'll have some time for questions. There are barriers to the application of additive manufacturing in the industry. These include the size of the part. You'll see that a lot of these parts, not including the house and not including the car, are kind of limited in size. 3D printers are generally not that large. Okay, maybe the largest 3D printer, they have a BAM, big area additive manufacturing printers that can print a little bit bigger, but part size is one of the barriers to this. There are hidden costs, as we talked about with sintering and post-processing. Also, materials can be very expensive for 3D printing. One of the bigger areas that companies are having difficulty with is ensuring part quality and regulatory part compliance. So both of these areas are difficult to assess because when we print something, we don't really know how the print process is going while it's being printed. So we don't have a good record for what happened to the material during the printing process. And this is a problem. Nobody wants to get in a car where we're not quite sure whether the axle is going to hold up. We certainly don't want to get into an airplane where we're not sure whether the bracket has porosities in it that we didn't detect. Companies are finding a way around this by doing in-process monitoring. So they're actually monitoring the process of printing while the printing is being done to alert, to stop, to do anything to fix this. Now, the aerospace industry right now has received full FAA compliance for certain parts, which means that the regulators have said, yeah, let's go with this. This is good. So that's a huge step. We also need skilled designers, right? We don't have right now a group of engineers that know how to design additively. That's still such a new process. It's not being introduced in design schools and engineering schools. How do we leverage the additive process to really make parts that are, beyond what we've ever experienced? Part reproducibility and consistency, that's an issue. If we print two parts on the same machine, are they the same? You know, are they made the same, or do they have the same porosity, strength, durability, toughness, all those issues? And finally, the old process, the old question of, hey, which process is better? Should I do metal? Should I use powder bed fusion? Should I do directed energy deposition? Which way should I go with this? And then which materials are going to be best? This is the future of additive manufacturing. Right now, the barrier to metal 3D printing is cost. That's one of the hugest barriers. Right now, the cheapest metal additive 3D printing machine is at least $250,000. This company, Mark Forged, has come out with a metal 3D printer under $100,000. They call it desktop metal. All right? The machine is just basically as big as this podium. And you can print metal parts. Did you pass that one around?
Yeah,
so the metal part that's going around right now, it looks like a handle for a motorcycle. That is a part printed on one of these machines. It's made out of stainless steel. It's 99.7% dense. It took between 4 and 6 hours to produce. And as you can feel when you get it around, it feels like a solid metal part. It is a solid metal part. Last couple parts I'm going to pass around. This is one of the machines that we have. These actual parts right here, for those of you that think that plastic 3D printing is kind of delicate, these parts are printed with Kevlar bands infused in the material. So these are very, very stiff parts. I'll pass these around. These are also prepared with fused deposition modeler. This is a fused deposition modeler. Hopefully we'll be getting, I'm trying to get one of these machines right now for us, so we'll see how that works out. Last thing is, I'm going to do a little ad for my department. If you're interested in this, we offer several classes in this arena. We have a class, Introduction to Additive Manufacturing, where we go through all of this for 17 weeks. We do a deep dive in every process, find out what makes each one tick. Then we look at the applications, industrial applications for each one over the second half of the class. So we get about as deep as you can in each process. Then we have a second class, which is for designing parts. So the second class, Design for Additive Manufacturing, is where we're going to get into the CAD system and we're going to start building these parts out of plastic, hopefully out of metal, and we're going to see what it takes to really design for additive manufacturing. The specialist certificate, which I am preparing and will be offered starting in the fall of next year, is going to be an additive manufacturing specialist certificate. It's going to be those first two classes plus your choice of either the introduction to 3D modeling with AutoCAD or the introduction to 3D parametric modeling with Autodesk Inventor. So if you're interested in finding out more about this stuff, you can sign up for the 125 class, or if you're really interested, you can complete the certificate. And I think that's it. So I guess we'll open the floor for any questions.
Questions? We have a microphone.
I think we went over a lot.
We might have covered everything.
Yeah.
That was so
Any
thorough.
questions? Yeah, question right here. Oh, hold on. Sorry.
Yeah, one of the questions I had. Remember when they were printing the house? What was the what's the advantage of 3D printing a house rather than just having original concrete based?
You want to take that?
Sure. The main advantage is time. That house took 24 hours to produce and to build and cost something like $10,000, I think they said. So they're really kind of gearing it towards low-income housing or to emergency shelters, stuff like that. Hopefully in a couple of years they'll start using it more for traditional housing, but that's really where their main focus is.
It's also a very it's a very solid construction. So insulation is going to be very good in that. It's going to be very thermally sound.
Good question. Oh, now they're getting more brave.
So as for the artificial lens, were there like any negative side effects that came from like using those artificial lens? Like they say like how you can make like, artificial arms, or you can make artificial hearts or anything like that. Like, were there any negative side effects from those?
Well, one of the big factors with artificial limbs is fit. You know, anybody that has a prosthetic will tell you that if it doesn't fit right, you're going to have chafing and discomfort, and it's really a huge negative. You don't want sores in that area. With 3D printed parts, you can scan it so you have a perfect fit. You literally can't get a better fit. Plus, if any change needs to be done, it's just a process of going into the CAD system, changing what needs to be changed, and printing it again. So it's not a full-blown manufacturing and production process. So I haven't heard of any negative side effects for that.
Not really, no.
The plastic is very strong. It's lightweight. There was another story that we didn't get in here, a little girl that has a disease that makes her bones very brittle. They printed a 3D printed suit for her out of plastic that enables her to stand in her classroom and to interact with kids. And the great thing about that is they can print as she grows, they can keep printing and printing, you know, different sizes. So she's able to, you know, basically partake in society.
Right. And not just plastic, they can also print titanium parts for like a knee replacement or a hip replacement.
Titanium the body doesn't react negatively to titanium. That's why titanium is used inside the body. There was another question here. Yeah. Wait for the microphone.
What would the building code implications be of the 3D printed house? Do you know?
That's a good question.
I think you would definitely, if you wanted to start printing one of these in Lamont or LaGrange, you'd probably have some curious looks and have to make a couple trips to the city planning office. But I think really this is made out of concrete. That's all it is. Basically, that machine is just a giant toothpaste dispenser spewing out concrete. So really, once they look at it, it's going to have the same strength as a concrete home. So yeah, I don't see any problem with that. But you would, you know, you'd have to go and explain it to them. Yeah. Any other questions? Yeah.
How much is like a basic 3D printer, like the most basic one you could possibly buy?
You want to?
Yeah.
Jordan has a couple of 3D, well, one at home, right?
Well, not that
Okay,
rich.
Okay.
You can go anywhere from like $100 all the way up to like $2,500. Some of the more basic ones, you really get what you pay for in terms of 3D printers. A good one, they start around $600. You're really paying for the quality, so that like a couple months down the line, your printer doesn't break, and then you're left with junk.
Yeah, and these are all plastic printers. The ones that we have, which are a little bit more robust than the home ones, the VAT photopolymerization one and the one that prints the Kevlar, those are $5,000. And then the larger one that we have, the big FDM machine by Stratasys, is about, I think it was about $14,000. So there, you know, that's not cheap. You know, it's nothing that I can buy, but it's certainly not a barrier to a company using those. Those are all metal, though. Those are all plastic. The lowest cost metal one, as I said, is right now $99,500. So if you got that amount of money burning a hole in your pocket, talk to me. I'll hook you up. I'll give you a place to put it. Yeah, question?
When you were talking about the time restraints for 3D printing, are there any developments in like being worked on right now that could possibly make it a faster process?
You want to talk about do you know the clip process? Remember the one that prints in 30 seconds?
Well, yeah, but that's not for like traditional.
Well, yeah.
printing.
So they are trying to shorten that time frame. The biggest problem with shortening the printing time frame is solidification of the previous layers. Right, you can't print the next layer on top until the first layer is done. Now there is a process in the VAT photopolymerization scheme called CLIP, continuous liquid interface printing, and they can print full models in about 30 seconds. All right, but those are plastic models. They're used for prototyping, and right now that hasn't really moved to the industrial kind of sense. So it's kind of in the experimental stage. You can buy them. They're not experimental like you can't get a hold of them. They're experimental in terms of, gee, this is cool, but what am I going to do with it?
Right.
Yeah.
Sounds like a question online, or well, something unrelated. But say if you were to 3D print something and you were put on AutoCAD and like they have like different colors or something like that, would 3D printers be smart like enough to like input different colors if you put in like the type of plastic?
Absolutely. There are different types of 3D printers that can print in color. So you can specify which faces of your part you want to have in color, and we should have put that in there. The ones that are full color.
Yeah, they have full color. You can print full color prototypes, you know, of whatever. There's several processes that can use color. So color isn't, in the metal printers, we can print tool steel, titanium, aluminum, Inconel, which is a nickel alloy. We can print stainless steel, like the part that's going around. So really materials, you know, that's kind of already robust enough.
Any more questions?
Could the printers here at school be able to print out parts to build a printer?
You mean like some kind of Terminator, like end of the world scenario? Well, I don't want the machines to hear this, but yeah, they could. We could print parts to. There are 3D printers that you can buy or that you can download that you 3D print the parts for your 3D printer. So yeah, we could absolutely do that without a doubt.
There are lots of self-replicating printers.
Yeah. Self-replicating, that's a good word for that. Self-replicating.
Rep.
And then we can just sit around in our bed and have machines give us drinks and food, and we don't have to worry about anything. Any other questions? All right.
Round of applause for Chuck and Jordan.
Thank you.
And we hope to see you all next month. We'll have a retired chemist give a lecture about climate science and climate change on November 14th at 11 a.m. So we hope to see you all there. Thank you.